all, this is a working project that I'm still working on. And this is a joint work with my doctoral advisor, Alec Kirschwell. Oh, Lisa is here. You have to unmute. Lisa, I think you should unmute.
My apologies to everyone for being late. It's been one of those mornings, and I'm deeply sorry. But I will quickly do an introduction because we're 1 minute late starting, and would like to say how pleased I am to introduce Hubeyb Gurdogan, my friend and collaborator. He's a PhD student at Florida State University, working with my old friend and longtime collaborator, Alec Kirschwell, and he's going to tell us about my new favorite shrinkage operator, multi-anchor point shrinkage for better betas. So I'll be back later with questions and comments, and for now I will mute myself again and turn over to Hubeyb.
Yeah, thank you, Lisa, for kind words and also just inviting me to this seminar. So yeah, as for acknowledgements, Lisa already said that we are collaborating on this project, and also Dr. Alex Shkolnik is also a collaborator for this project, and Dr. Kirschwell is my doctoral advisor. And so let's, this project is just a continuation. To me, it's a continuation of a paper that is called Dispersion Bias paper, written by Dr. Shkolnik, Dr. Goldberg, and Dr. Papanikolaou. So it has lots of commonalities. So we're going to use the same foundational structure. So let's begin with my plan. Okay, I'm using an annotation tool here. So how do I go to the next slide when I'm using the annotation? Let me go to this one. Okay, yeah. All right, yeah. Here we start. So, okay, I will go with the problem formulation and the model and the covariance matrix estimation. That is the GPS treatment. So the bullet number 1, 2, 3 are going to be very common with the dispersion bias paper. It's going to be my exposition to the dispersion bias paper and my interpretation. And then we're going to introduce the multi-anchor point shrinkage that I call MAPS estimator. And we're going to introduce the theorems related to the performance of MAPS estimator. And we're going to do a numerical study of MAPS, just comparing its performance with the GPS and some other operators. Okay, so let's get started with the motivation and the problem formulation. Since Markowitz in 1952 introduced the modern portfolio theory, it is very common, and it's, the finance practitioners have been using the mean variance optimization to calculate their portfolios. And what they do is they use an expected return vector mu and a covariance matrix that they have, and then they employ quadratic programming to come up with that portfolio that they think is a good portfolio. And the focus of this work will be not a specific point on the efficient portfolio, which is the minimum variance point. That is the left tip of the efficient frontier. So why do we consider the minimum variance? There's a theoretical reason and there is a practical reason. The theoretical reason is, so our aim is to understand, first of all, how covariance matrix is distorting the portfolio weights. So when you use a covariance matrix that is different than the actual covariance matrix, which is not available, then that's definitely going to distort the portfolio weights, and we want to understand that. If we introduce another if you introduce a return target, that means we are introducing an expected return vector, which is also containing some errors. So we want to deliberately isolate that error to see exactly how covariance matrix is distorting the portfolio weights. That's one theoretical reason. And does that have any match in the practical world? Yes. So people are using minimum variance portfolios to trade. So there's like a iShares Edge minimum volatility ETF. I checked it yesterday. It was like 33 billion of worth of net assets being traded as of yesterday. So it's still being used. Right. So having this motivation, the problem is, so we are looking at a minimum variance portfolio under fully invested constraint. This is the budget constraint. And this is the portfolio that is having the minimum variance. So in practice, this covariance matrix, capital sigma, is not available and has to be replaced by an estimator. Let's call it like sigma hat. And that is creating a portfolio that let's go W hat that is subject to the estimation error. And so any error that we do in the covariance matrix estimation is going to have a direct impact on the portfolio. So we have to be careful. So, and here's a historical quotation regarding the fact that we should be careful in selecting these covariance matrices, even though it is obvious. But yeah, Harry Markowitz already said that in 1952 when he introduced the EV rule. Okay, so the aim of this work is to come up with an estimator of covariance matrix, where the resulting portfolio in the optimization problem is close to the actual portfolio in this risk metric. Okay, so we don't consider the L2 error because it doesn't have anything to do with the money. So we are looking at this risk metric to see how distant our estimated portfolio from the actual portfolio in terms of the risk characteristics. Okay, so this is the tracking error that we're going to use to just quantify the quality. Okay, so here is the underlying model that we look. We are looking at one factor model of P securities. So left-hand side, we have a return vector of P securities, and we have this one factor equation. Beta is unobserved and non-random constant. And capital X is holding the market return, and capital Z is holding the asset-specific returns. So by the way, so just feel free to stop me if there's any question. I'm okay to be interrupted. So that is the model that we are considering. And so we are going to consider the scenario that we have lots of assets, like, and very limited number of observations. So we're looking at the regime that number of securities is exceeding the number of observations. That is happening in a practical, that's happening in a lot of times in the practical applications. And to make a reflection on this situation, we are going to study the asymptotic regime that we are sending P to infinity, and N is staying finite. The N is the number of observations. So this is the regime that we're going to study. Okay, and if there's no questions, let's go to the assumptions that we make. So we have like 4 assumptions, and they are to actually support the theoretical results, mostly mild assumptions, but I want to stress the assumption number 1. So the entries of the beta are uniformly bounded. This is a mild assumption, because I mean I have never seen a beta that is like huge. So we are assuming that the betas are uniformly bounded in even the asymptotic regime, and the mean is defined by the mean. So this is the mean, and dispersion is defined by this. So beta is non-random, but this is basically replacing, I mean, some sort of standard deviation for non-random vector. This is like relative to the mean, the standard deviation. So the assumption about them is we're assuming the mean is in the asymptotic regime staying away from 0 and finite. And we assume that the limit exists and limit will be staying away from 0 and has to be finite. And same for the dispersion. Okay, and let's go next. So this equation is very similar to our model equation, you might notice. But here we are just writing down an equation that the model imposes on the data structure. So we are just considering n subsequent observations of the market. So, and for each observation, the model is going to actually trigger, I mean, when we use n observations, model will trigger this equation that is no longer vectors. This is like a p by n vector that is holding, in each column, it's holding a p vector of returns. So since I have n observations, it's going to be p by n. And similarly, adjustments are made here. And one thing is, so we are just assuming that the observations are identical to each other in terms of randomness, identical and independent. Okay, so we had a one-factor model that is implying a rank 1 covariance matrix of this type. Here, one important thing is B is now this is the normalization of the beta. This is living on the sphere, p-dimensional sphere. And sigma beta squared is just sigma squared, the market standard deviation times the norm of the beta. Okay, so this is what the model is actually implying. And here is the data structure that is following from that is actually using the data structure. The dispersion bias paper is proposing this class of estimators that is basically sigma beta hat square is replacing sigma beta square, and delta hat square is replacing delta square here, and H is replacing B. So they are like estimators of each other. So, and sigma beta hat is prescribed in dispersion bias paper after long theoretical discussions. That is the gap between the largest eigenvalue of the sample covariance matrix and the mean of the remainings. And similarly, delta hat square is also prescribed to a fixed value. That is n over p, the number of observations over the number of assets, times the mean of the eigenvalues when you extract the largest eigenvalue. Okay, so we are going to discuss a few things about these two estimations and how they are reflecting on the tracking error. But we are in this class of estimators, sigma beta hat and delta hat are already prescribed, and H is free to choose for us. So,
sorry, quick question. I has a upper script 2, a superscript 2. Is it the average of the remaining values or the square of the average of the remaining values?
That is the average of the remaining values.
Okay, thank you.
Yeah. Okay, you're welcome. So let's go to the next one. So given these class of covariance matrices, they're going to trigger two portfolios, one for the actual covariance matrix and the other for the class of estimators that is proposed in dispersion bias paper. So before anything, let's actually define what Q means. Q is the normalization of the E vector, either the vector that has all ones, that is now living on the sphere. And I'm using this bracket x comma y for the inner product. Okay, so regardless of what covariance matrix we are using, this is true from calculus. These first equations are true from calculus. Since we have this rank 1 structure in the covariance matrix, the inverse is inverse has a closed form solution. For that reason, we have a closed form solution for the portfolio, and similarly here. If you look at the ingredients closely, we see that k hat is replaced by k, and actually k is replaced by k hat, and b is replaced by h here. So where k is the ratio of these delta square over sigma beta square, and k hat is the estimator of that. So good thing is it is proven in dispersion bias paper that k square and k hat square are both going to 0 with rate 1 over p. So in the tracking error, they're going, because of this reason, in the tracking error, they're going to vanish. They're going to actually disappear in the tracking error. So if you want to blame a bad covariance matrix of this class, the blame is on H, not on delta hat square or sigma hat square. So H is the driving factor of the covariance matrix of that class. So, okay, when we look at the tracking error following the formulation in the dispersion bias paper, so it has this form, okay? So we have a constant here, and this term is called the optimization bias term. And this term is called the secondary bias, that we call this one secondary bias. And this has the same characteristic, same asymptotic characteristic with the optimization bias over P. Okay, we're gonna look at them closely. So if there is any error in the tracking error, so it's going to come from this, I mean, the significant errors will come from this one or this one. Let's look at them closely. So in the, yeah, so if you set H to the PCA estimator, that means the first principal component analysis factor, that is the eigenvector corresponding to the largest eigenvalue of the sample covariance matrix, then due to a theorem in the dispersion bias paper, we have the optimization bias term that were like present in the tracking error is almost surely finite. So that is a significant term. So on the other hand, if you look at the secondary bias term here, this has a 1 over p, right? So this is very likely that this is not significant compared to something that is staying finite in the asymptotic regime. So then GPS method is focusing on minimizing that optimization bias term. That is the most significant term. So there is a very nice geometric representation of the optimization bias term. I want to actually go to the next slide. I have a hand drawing that I want to actually share. I'm a little bit nervous because my Calc 1 students never likes my hand drawings, but let me give it a try here. So, okay, here's the formula. Let me explain what this means. So if you remember the optimization bias formula that was like given in terms of these inner products. So, and this can be rewritten by this, and where the theta appears here is this angle between geodesic connecting HB and HQ. So remember, Q were on the sphere, B were on the sphere, and H is an eigenvector, so already comes as a normalized. So this is also on the sphere. So this theta is the angle between HB and HQ. And this theta HB is if you consider the origin and look at the central angle of this geodesic, this is theta HB, okay? All right, where does this comes from? This is coming from the cosine rule in the sphere. So, okay, this is the formulation. And if you look at here, what would be the desirable thing? We would desire theta to be 90 degrees, because if theta were 90 degrees, then that would vanish. So the optimization bias would vanish. That's the desirable thing. So just for that reason, the GPS method is taking the spherical orthogonal projection of P onto the geodesic connecting H and Q, so that they get this 90-degree angle that is going to vanish the optimization bias term. So this point is called HQ, H sub Q. I mean, in this presentation, this is what's called the Oracle estimator of the GPS method. Okay, let me drop this annotation and go back. How do I erase? Okay, yeah. All right, so we actually talked about why they are actually doing this spherical orthogonal projection. That is what the GPS estimator does. That is the Oracle estimator. So officially, what they do is they are actually landing on a point on the geodesic connecting H and Q, right? So, and this is the parameterization of that geodesic. And the point that they land on is the point where t equals this number exactly. This is easy to calculate. And if you look at this one, this parameter t, one thing that is catching the eye is the b comma q. If you look at b comma q, this is the inner product between b and q. What's wrong with this is nothing wrong with this, but the b is unknown. So how do we know if b is unknown? How do you know HQ? So for that reason, they come up with a data-driven estimator that is actually converging to the Oracle estimator, which is, I think, remarkable. So for a second, just bear with me. I will just explain what this tau is, okay? And the theorem in the paper says, so if you actually replace this Oracle estimator, remember Oracle estimator were already vanishing the optimization bias, and when they replace this Oracle estimator with their data-driven estimator, in the asymptotic region they get 0, which is I think remarkable. So even though we don't know B, we are able to come up with HQ hat. Let me explain how do they actually turn around this. So okay, for that let's define some notation. HQ sub infinity, HQ is already the inner product, right? HQ sub infinity is the limit of this inner product as p goes to infinity in the asymptotic region. And HB sub infinity and BQ sub infinity is defined similarly. Okay, and so here's the theorem that is giving rise to the data-driven estimator. So let me first focus on this part. So HB sub infinity is equal to phi psi sub infinity, that where psi p is defined by this equation. So this is the gap between the biggest eigenvalue and the remaining eigenvalues divided by the biggest eigenvalue and square root. This is completely data-driven, and what is remarkable is this one is catching the inner product between H and B in the asymptotic region. So even though you don't know B, when you use the PCA estimator, you know how much error you are making, because inner product means, if you know the inner product, that means you know the L2 error, right? So even though you don't know B, you're able to know how distant H is to B. So, okay, HB can be replaced by phi P as an estimator. And if you go to the next equation, so if you can use this equation, this asymptotic equation, to actually come up with an estimator of BQ, right? So you can divide HB from both sides to get HQ over HB, and replace the HB by phi P to get an estimator of BQ. So, and if you go back, the problem is resolved here. So BQ is replaced by HQ over phi P, and HP is replaced by phi P at any place that they appear, and then you're going to get this tau, which makes this data driven. And the best thing is this is converging to HQ. Okay, so let's talk about the aftermath of the GPS fix. So there's a conjecture in the dispersion bias paper that they also do some simulations to validate. What this says is that we already know that this is converging to 0, right? The optimization bias goes to 0, and they take one step further and look at P times the optimization bias. And in average, this is going to stay finite. That's what it says. So then if we go back to the secondary bias, we were like we didn't like this secondary bias because we didn't want to actually focus on this one because it was order 1/p. And at that time, before the GPS fix, optimization bias were finite, right? It was significant compared to this one. But after the fix, they are like comparable because of this conjecture and the numerical simulations. So then what we can say is, if you're able to come up with an estimator that is maintaining the success of the optimization bias term, maintaining the success of GPS on the optimization bias term, and also trying to reduce this error on the secondary bias, that is going to actually improve the GPS comparably. So, and the question is, how would you actually try to reduce this? And the answer is simple. So if you get H, your estimator of B, close enough to B, then this term B minus HB squared will actually vanish, right? So not vanish, but will get smaller. So if you get closer to B, then you're gonna get smaller error in the secondary bias. So okay. Let's actually reinterpret the GPS method geometrically to be able to come up with a generalization of the idea. So we already discussed that GPS is doing the spherical orthogonal projection on the geodesic. So what it does is, as a result of that, it is picking up the point, the oracle estimator that is closest to B on the geodesic. So basically, it's picking up the closest point on the geodesic. And also as a result of the orthogonal projection, the angle between HQB and HQQ is 90 degrees. Remember that theta angle? So that is set to 90 degrees as a result of this orthogonal projection. So what we claim here is that is equivalent to the following procedure. So taking the orthogonal projection of B onto the linear subspace spanned by H and Q, and normalizing back to the sphere. So that is the claim. By the way, how am I doing regarding the time? What time is that?
Yeah, so Hubeyb, the seminar goes until 12, well, you're in the East Coast, 3:30 your time. And so please feel free to take as much of that as you want, but good to leave time at the end for questions, 10, 15 minutes
so
in case.
How many minutes do I have?
So it is according to this, so it's like 11:40, it's 2:40. So you have another bunch of time.
Okay, yeah. So, all right, then I think I have time for just showing my drawings. So I want to actually illustrate why this is equivalent to, why the spherical orthogonal projection is equivalent to this two-step procedure. So one thing that we may want to show, we want to show is we are picking the closest point and we are just keeping the angle 90 degrees. Okay, so if you prove that, then we are done. So let's first show that this procedure, this two-step procedure is actually picking the closest point to B on the geodesic connecting H and Q. So let me just introduce you to the picture here. So B is our point B, and here is the Q, the North Pole, and here is the PCA estimator H. And this circle is the geodesic connecting H and Q. And here is the center of the circle and also the center of the sphere, the origin. And the two-step procedure, we're just taking the projection of B onto the linear subspace generated by H and Q. Let's set it to X, the projection. And by Bessel's inequality, just keep in mind that H and Q has the norm 1. By Bessel's inequality, X has norm 1. That means it is staying in this circle. So let's then illustrate X in here. So the first step is just having this projection along this red dotted line. And then the next step is just normalizing back to the sphere. So since it is in the circle, when I normalize, it's going to end up in the circle, which is on the geodesic. That is, I do by just starting from the center and walking along, well, walking towards X and continue until I hit the circle, which I call Y. Okay, Y is X over the norm. And the goal is to show BY is actually, the distance between B and Y is actually smaller than any point that you pick for, I mean, the distance between BY prime, for example, for any point you pick on the geodesic. Okay, so the starting point is, if you consider this point X, this is easy to see that the closest point to X on the circle is the point that you get by walking along the point connecting the center and your point that you start. So and then just marking the point that you hit the circle. That is the closest point to X. So XY, the distance between XY is less than or equal to XY prime. This is just the length of the edge, length of the side. So that is one thing. And the other thing is this triangle BXY is just a 90, this is a right triangle where the angle BXY is 90 degrees. So we have a Pythagorean theorem, and similarly we have it for BXY prime. So we write the Pythagorean equations, and since XY prime square is bigger than XY square, we get BY prime square is bigger than BY square. So that's one thing. So we are really picking up the closest point. And the other thing is, do we have that angle theta equals 90 degrees on the sphere? So for that, we are going to employ the cosine rule of cosines on the sphere. So just consider the triangle BYQ. And the rule of cosine says cosine theta is equal to this expression. We don't care about the bottom. We want to show that cosine theta is 0, right? So if we show that the numerator is 0, then we are done, right? Okay, and what do we use? We know that B minus X is perpendicular to the linear subspace generated by H and Q, and Y is on that linear subspace, and Q is on that linear subspace. B minus X is basically perpendicular to Y and Q. For that reason, BQ is equal to XQ, and similarly, BY equals to XY. And XY, if you just substitute Y by this, you're going to see that this is the norm of X. And what do? We just substitute these two identities into this numerator. BQ is substituted by XQ, and QY is staying same, and YB is substituted by norm of X. And just do substitution. Just substitute Y by X over the norm, and you'll get this term is equal to this term, and you'll get 0. That's confirming that theta is 90 degrees. Okay, so basically there are two equivalent procedures. And now, so what did we do so far? We reinterpreted the GPS methods. And now for a good reason, we are going to revisit the assumption 1 that we stressed at the beginning. So let's look at its effect on the inner product between B and Q, okay? So inner product between B and Q can be rewritten as the mean over the norm over radical P. So at this point, given that the mean is not vanishing in the asymptotic region, we can confidently replace this by this formula, okay? And BQ hat is equal to 1 over 1 plus dispersion squared. So in the square root. Since this is assumed to be not away from 0 and finite, that is going to ensure that the BQ infinity is away from 0 and away from 1 in the asymptotic region. So if this were 0, then we would get the BQ infinity will be 1. And also if mu infinity or mu p at any point would be, if it were 0, then we would get BQ equals 0. So so at this point, just note that we are not questioning the validity of these assumptions. They are empirically validated. Actually, when we look at the stock market, when we look at the stock market and look at the HQ, it is actually closer to 1 and never vanishes. So if HQ never vanishes, then BQ is not going to vanish too, because of that nice asymptotic results that I showed earlier, that is connecting HQ and BQ in the asymptotics. So okay, so let's think about the otherwise to see what that assumption brings us. So if we had BQ infinity equals 0, then let me actually recall this asymptotic result. So HQ infinity were like BQ infinity times HB infinity. So if BQ infinity were 0, then we would get HQ infinity also converging to 0. And that would imply that the GPS estimator is landing on the PCA estimator in the asymptotic regime. Let me illustrate why that is true. Let me drop this annotation. Okay, so all right, so if you remember, HQ hat were equal to this parametric equation where tau is equal to this. Let's actually play with that and replace HQ by 0. That would set tau equals 0. And what would happen when tau is 0? Then this will be just h over the norm of h, which is just h. So then that says that HQ hat is just landing on h. So that says asymptotically there's no improvement in terms of alto error if we had BQ infinity equals 0. So then we can make this conclusion that having BQ hat in 0 to 1, just staying away from 0 and staying away from 1, let the GPS estimator to be able to create something that is closer to B. So as a matter of fact, Q is a special point. That is also empirically validated. So Q is actually elevating us to come up with an estimator that is closer to B. Let me erase these markings. All right, so that's what I'm saying here. So if we have more points like Q that can be used, if there are like more points like Q, then we can use that to generalize the GPS estimator in terms of in favor of improving the alto error. So remember that reinterpretation that we do about the GPS estimator. What we were doing, we were just taking the B, projecting on the linear subspace generated by H and Q, and then normalizing back to the sphere. So if we have more points like Q, then we can actually enlarge that subspace that we are projecting on, and then we can get something closer to B. So in that regard, we are just considering giving a linear subspaces, sequence of linear subspaces. We are defining the HLP, the maps estimator, by projecting B onto that subspace generated by H and L and normalizing back to the sphere. That I consider this as a generalization of GPS. So if we were having LP just empty, then we would actually recover HL equals H. If we were actually having LP equals the span of Q, then this linear space would be just H and Q. And we already showed that that is the GPS estimator. So in these special circumstances, we just recover the GPS. Okay, and one other, so we have something here. So we are saying that this maps estimator is actually vanishing to optimization bias too. That's just because what I showed earlier, that theta angle is 90 degrees when you do this two-step procedure. Okay, I mean actually the validation is same in that regard. Okay, so and just at this point, if you have questions, I mean, I already said that I am happy to be interrupted. if you have questions, I can take.
Any questions?
If not, I'm also happy to continue.
Yeah, okay, go for it.
Yeah. Okay, so let's look at the L2 error here. So for this new maps estimator, so B minus HL, if you look at the L2 error, at the end, it becomes 2 times 1 minus the length of the projection that we do on the H and LP. So from there, we can conclude that if the length of the projection increases, then the quality of HL will, I mean, if the length of the projection increases, then the quality will increase because you're getting closer to B, right? And what does that depend on? So if your LP, your vector space that you're projecting on is close to B, then you're gonna get a better, bigger length, right? So that is just depending on the availability of the points in L, and I'm calling those points anchor points. All right, and then if we have Q is included in L, then this subspace has H and Q inside of itself. Since we are enlarging the subspace, it is natural that we get something closer or equal to B. I mean, something closer to B or equal in terms of something that has the same quality of the GPS estimator or better quality. So because we are enlarging the subspace that we are projecting on. Okay, so now we have to consider how we select this subspace L. So if, for example, you select L equals RP, all vectors, the whole vector space, then at the end you get HL equals B, but obviously we cannot just turn this into a data-driven estimator. So obviously we have to keep the size of L smaller so that we can have a data-driven estimator. So let's go for the data-driven estimator, which is here. So we are just under these assumptions. We are also assuming that this subspace LP is independent from the asset-specific returns, and we are imposing a bound on the dimension of LP. So we don't want it to be converged to infinity faster than p to the alpha, where alpha is smaller than this quantity, that is where R is coming from the moment conditions that we put on the capital Z. Okay, so given that, we can have a data-driven estimator of this sort that is converging to HL, the oracle version of the maps estimator, almost surely in L to norm. Okay, so in principle, this is mimicking the GPS data-driven estimator. And there's like two asymptotic convergence results that is making the construction of this data-driven estimator possible. First one is the one that is proven in the GPS paper, the dispersion bias paper, that the psi p is converging to HB infinity almost surely. And the other one is this following. So if you look at here, so under the similar assumptions, we are saying that the projection of H onto L is converging to this scalar times the projection of B onto L. So geometrically, what does that mean? If you project H onto L and then normalize back to sphere, and if you project B onto L and normalize back to sphere, these 2 points on the sphere asymptotically converge to each other. I mean, one point is converging to the projection of BL and normalized version. So because the scalar is just going away when you normalize back to the sphere. So that's the geometric interpretation. And let's now, so at this point, we're going to illustrate some theorems regarding what happens regarding the different scenarios of selection of L. So this is the asymptotic assurance theorem. So no matter, I mean, as long as you include Q in LP, your subspaces and put that bound on the dimension, we are going to be either doing same or better than the GPS estimator. That is the asymptotic assurance. But this is going to happen in the asymptotic regime. So here is, I'm just putting some explanations. Enlarging the subspace. So there's like a downturn. When you enlarge the subspace, that's going to put more elements of Z into HL. But in the asymptotic regime, they clear out, given that the dimension is relatively small. Okay. So that was the performance of general maps estimators, as long as you put Q in those subspaces that you're projecting on. Here is the, I'm going to illustrate a random selection scheme of capital L, the subspace. So for that, we are going to define something called the Haar random subspace. So we are just propagating that subspace with this random variable. It's taking values in the orthogonal group and inducing the Haar measure on the orthogonal group. How do we propagate the subspace from this random variable? Basically, we're applying this to, we're just letting this act onto the Cartesian basis elements for Kp many of them. Then we say this is a Haar subspace of dimension Kp. Note that, so by the virtue of the orthogonal group, at the end, you're going to get an orthonormal basis. They're like linearly independent when you actually propagate the subspace by this. Okay, so let's talk about its performance. So when you actually have a random subspace that is propagated in that way, and have this bound on the number of anchor points, and if you don't inject Q into HP, if you don't inject the North Pole, then you end up having the same performance of the PCA estimator in terms of the L2 error. If you actually insist on putting Q into your linear subspace, then at the end, you're going to land on the same quality of the GPS estimator. So that means if you use the random subspace of that sort, that's not going to improve over GPS estimator. So now let's consider another type of selection of linear subspace. For that, we're going to introduce something we call partition. So we're considering this index set 1 through P. We are denoting this calligraphic P by a partition of this. That means non-empty collection of non-empty subsets of this one that is having the union equal to this index set. So we are just calling each element of this partition as atoms, and number of atoms by the absolute value of capital P, I mean the calligraphic P. And we will say this partition is beta ordered if for any distinct atoms, these atoms are completely separated in terms of beta ordering. That means maximum of one is less than the minimum of the other. So, or vice versa. So as an example, if you're given this set of betas, then examples of beta ordered partitions would be example 1, 3, and 2, 4. So 1, 3, notice that first one and third one is the biggest two, and second one, fourth one are the smallest two. So they are like completely separated in terms of ordering. So sorry. So then at this point, in order to be able to have this partition, do we have to know the whole ordering of the betas? We don't have to know the whole ordering, because we are not interested in the ordering within the atoms. We just want them to be separated. So, and using this partition, we are defining a vector subspace. So, okay, for any subset capital A from the index set, we can define a vector by putting zero weights to the entries that is belonging to the set A, and putting non-zero weights, that is this one over radical of the number of elements, to the entries that are included in the index set capital A. That is how we define a vector given a subset. And then given a partition, then we're going to define the linear subspace generated by these vectors by this. So for any atom, we define a vector with this way, and then for a partition, we come up with a linear subspace. As an example, if you consider this partitioning, so this becomes 1 over radical 2 and 1 at the first and third location, and similarly 1 at the second and fourth location that is corresponding to this atom. Okay, that's how we come up with this linear subspace type. Okay, we call it beta order. So, and then we're going to look at the performance now. So we consider a beta ordered partition that is having number of atoms as p to the alpha, and this one is ensuring that the number of elements in each atom are like close to each other. Okay, so example of such a partition that has this set of conditions is, for example, for p equals 100. For example, if you just set radical p, the number of atoms, putting the first 10 securities with the highest beta into the first atom, and next 10 into the second atom, and next highest into the third atom. So this is a partitioning that is satisfying these conditions. Okay, and if we have such an information, then we show that limit as p goes to infinity, the L2 error is going to 0 almost surely. So like a partial ordering is leading to this. Okay, so and the question is we're going to answer this question later, but the question is, what happens if we don't know the ordering, which is what is the case. So in that case, we're going to come up with some observable separations in the industry, and I'm gonna illustrate that later. So first, at this point now, I'm going to just illustrate the numerical study that we've performed. First, we're going to illustrate the performance in the simulations. We're going to confirm these theorems, and then we're going to look at some data to illustrate a data-driven estimator that is using not the beta ordered partition, but a data-driven partition. Okay, so our numerical experiment is using market return from normal distribution, and this is the asset-specific return from normal distribution. And we're just drawing a beta with mean 1, and d beta is the dispersion. And we generate the return matrix according to the one-factor data structure. And we're doing simulations for calm, over calm, and stressed market environments. So for the calm, we just calibrate our sigma, delta, and d beta, the dispersion according to the calm and over calm settings and stressed market settings. For all these market conditions, we will explore this dimension, p to the 1/3, integer portion of p to the 1/3. Okay, so here is the, let me use an annotation here. Okay, here is the calm market simulations. This is the L2 error, and this is the number of the securities. And I actually didn't notice that this is beta ordered. I forgot to add that. And this is the random ordered. Okay, so if you look at here, so random ordering is in the asymptotic regime is capturing the GPS. At the beginning, it struggles, but then asymptotics kicks in and it gets to GPS. So that was one promise of the theorem. And this is the beta ordered partitioning. This is doing better than the GPS. And let's now consider something else. If you look at the L2 distance between B and Q, we can rewrite it like this. What is important with this equation is if we have the dispersion here very low, close to 0, then we would end up being very close to Q. So remember that linear subspace that we are projecting on. So Q is already in that subspace because Q is a good point. We want it to be in that subspace. If Q is already doing most of the work, then there's no much room for improvement, right? So if the dispersion is very low, then there's no much room for improvement. So, and we know that adding more anchor points into L is introducing more noise elements that we promise them to go away in the asymptotic region, but we should be careful when we are looking at the non-asymptotic regimes. For example, P equals 500, sometimes it doesn't kick in that fast. So, because that in the regime that in the situation that we don't have room for improvement, if you put lots of anchor points, then that noise elements may overshadow your small gains. So, okay, that is one thing. And let's look at the tracking error. What happens in the tracking error for the call market? So the beta order is performing well, and PCA is in the call market is similar to GPS, but just shoots up to infinity as shoots up after as number of securities is increasing. So that is remarkable about the GPS. And so let's look at the overcall market. So P equals 500 is the place that the asymptotics didn't trigger yet. So if you look at the L2 error, we were using large number of anchor points here. The beta, this yellow one is the beta ordered. So beta ordered were expected to be smaller than GPS and also the random, but it looks like it is bigger. The reason is we are using lots of anchor points and we are on the overcall market. The dispersion in the overcall market, or like call markets, dispersion is lower, and in the stressed market, dispersion is very high. So here the dispersion is low for that reason, and we used lots of anchor points for that reason. We actually the beta ordered partition is struggling here. So we have to be conscious about the number of anchor points. So, and then asymptotics kicks in, then it just takes its place, but it just takes time in the number of securities. Okay, and let's look at the tracking error comparison. Even though in the L2 error, the beta ordered partition failed, but in the tracking error, it's doing fine. And let's go to the stressed market. Stressed market is the market regime, market environment that both the GPS and the maps is doing best. So because there's high dispersion, that means there's much room for improvement. So then, so let's go to the tracking error comparison. So they do very well in terms of the tracking error as the PCA is shooting up. And now this is the last part that we are considering the simulations using over-the-counter partitions. So do you have any questions up to so far? No? Okay. All right.
I have lots of questions, but I'll save them to the end. Keep going, Hubeyb.
Oh, okay. All right. So consider a partitioning that is not necessarily beta ordered. And we just propagate a subspace using that partitioning. And we're going to actually analyze this subspace. So if you look at B minus the projection of BL, if you look at the L to distance, we can rewrite it like this. If we have this formula, so what does this say? This is going to be small if each collection, the betas in each collection are close to each other. That means they're concentrated around the mean. So if we're able to come up with a partitioning that concentrates the betas in each atom to the mean in that atom, then that means we are successful. So, and there are like lots of separations in financial industry. For example, low cap, half cap separation that puts betas that has similar characteristics into the same groups. And there's financial sector separation that puts similar betas into same groups. I mean, that we can try one of them to see if it's going to make any difference. So for that reason, we're going to use the sector separation that's in the S&P 500. There's like 11 sectors. We're going to use that separation to construct our partitioning and also our linear space generated from that. So we created, here's the experimental setup. We create a return data from 6 consecutive time windows that has 25 business days. The time range is September 1st to May 1st, 2020. For each time window, we create a PCA factor and normalize it to 1. That is going to be used as a beta. We treat that as a beta in our simulation. And from there, we generate a market return, and we generate noise matrix, asset-specific returns matrix, and then we generate the return matrix accordingly. In terms of the weather, first 3 time windows, we identify them as the calm market, and later 3 time windows as the stressed market that is due to COVID-19. So for the calm market conditions, we calibrate the sigma and delta, and being conscious of the fact that this is calm market, we are just using only 2 anchor points. We're putting the part where we are selecting a partitioning that puts betas into 2 groups. First group is infotech, energy, industries, and financials and materials, and the other group is the rest. For the stressed market conditions, we are using the full sector separation. We are just partitioning all betas into 11 subsets according to the financial sectors. And we are calibrating sigma and delta, and here's the results. So the yellow one is the beta ordered, and the purple one is the sector partitioning. This is completely data driven. In terms of L2 error, in the calm market conditions, L2 error is not doing a significant improvement. That means the sector separation that I used is not enough. But in the stressed market conditions, when we use the full sector separation, it is doing a significant improvement. So let's look at what happens in the tracking error. So it's just the L2 error mostly reflects here. But what's remarkable here is the PCA estimator in the calm regime. I think first one is not just calm, it's I think over calm. First one and third one. PCA estimator is almost doing better than both the sector separation and GPS. And then just notice that this is not a asymptotic regime. I'm just using only 500 stocks. So it may not kick in that fast here. So in first 2 and 3, they don't do very well, the purple one. But in the stressed conditions, the sector separation does very well, and GPS does well because the PCA is just shooting up the infinity. That is, let's say not the infinity, but it's shooting up. So that is the result regarding the tracking error comparison. So I think I'm done with most of it. So here's my future directions. So first of all, I want to understand, so far, any of our asymptotic results doesn't include the rate of convergence. If it were having rate of convergence, that we would be able to somehow calibrate the number of anchor points to the market conditions in a more precise way. And I want to use like different market-derived partitions, maybe high cap, low cap separation, or I could use clustering with machine learning. And the more importantly, I want to just I want to generalize this to multi-factor models. So I think that's all I want to present, and I'm happy to have your questions at this point, and any point.
Yeah, well, thank you, Hubeyb, for that talk. Are there questions? I have some questions, but before I try and ask them, maybe questions from others? I guess you have, even Nick's gone quiet, so there's a lot of information there. But let me start with a few. A question I had before that you answered in the course of your speaking was how you use this partition ordering in practice, and you've shown us an example with sectors. I'm wondering if you've taken, or if you're thinking of taking the empirical analysis to another level by looking at this working on actual returns instead of simulated returns. Then of course you can't use your tracking error comparisons and other simulation-based metrics, but maybe some other metrics could come into play.
Yeah, so that's also another future direction, possible future direction for me. So, and you're right, we haven't used the full empirical data. We just extracted the PCA factor from each time window, and then we used that to propagate the data that we have. So, and that's one thing that's lacking here. You're right about it.
Yeah, well, we haven't done it either, so we share but it does seem like a possible direction. Another question has to do with factor models. So in the factor modeling that I'm used to, factor loadings or betas or whatever you want to call them can be maybe time dependent, but they're usually not random. And you've introduced an element of randomness to betas. I guess you've made a bunch of assumptions, like maybe the random betas are independent of the returns to factors or something. Is this going on? I'm not familiar with literature that has random betas. I'm wondering if it's going on elsewhere, and what are the implications of this more general kind of factor modeling?
Yeah, so I mean, aside from betas being random, so if you look at the time windows, we know that betas doesn't stay constant. So that's one thing that I'm very concentrated on. And the other thing is, so this is like, if you look at the, what's that called? The conditional CAPM model, betas are random there. So, I mean, if we consider betas to be random, it is more close, this work would be more close to be conditional CAPM than the regular CAPM.
Okay, well, I should probably brush up on that. A final question that I have, so the initials GPS, it's kind of, we initially thought of them as related to global positioning system because we're kind of looking for something. We're looking for this eigenvector, B, a true eigenvector, when we only have a noisy approximation. And so finding actually some embedded biases in that approximation are letting us improve our detection of it. What are our chances? How close are we going to get? Like, you found a way that Alex and the two Alexes and I didn't find, to add more information to, in some cases, specific cases, improve our honing in on the true B by putting in, how much information do we need in this kind of setting to get it exactly, or are we ever going to get close?
Yeah, so I mean, one theorem that we have is if we have the partial ordering of the betas, then asymptotically we're going to land on exactly B. But we definitely don't have it. But it now, I mean, the question is how the industry specialists are right about the beta orderings. I mean, some market gurus may come up with like saying these betas are definitely bigger than the other betas, and if they are right, then this asymptotic result will trigger in. So, but maybe not. So I don't know the answer to your question. Yeah.
Yeah, it was sort of an interesting thing to consider. One of the regimes you were looking at, which is the COVID regime, between, I believe, February 19th and March 31st, we had one of the most stunning beta migrations that I've ever seen, with typical low beta stocks like utilities going from betas of 0.2, 0.3, 0.4, all the way up to 1, and higher beta stocks like our favorites, the FANG stocks, Facebook, Amazon, Microsoft, those guys, Apple and Google, coming down to beta 1 and even below. So there's been a lot of motion in betas, which hopefully information from markets can inform your theory, this rapid moving around, or no?
I mean, if you look at those regions, which is 5 and 6, I believe. So we got some improvements regarding the sector separation. So sector separation in that regime, I mean, in those times, we were able to actually separate enough the sectors in terms of beta ordering. I don't know how beta migration affected that, but it was like, even though there was beta migration, the dispersion was still high. So that is leaving lots of room for improvement. So
okay. Great. So those are my questions. So I'll open it up one more time to the group for further questions. See, there's stuff in the chat. Wow.
oh, I haven't seen it.
No, nothing here that I'm gonna relay. So what I'm gonna do, I don't know if you guys are familiar with all these great icons, but we can applaud the speaker virtually and physically. And Hubeyb, thanks for a really terrific talk. To all the CEDAR seminar participants, this is our final seminar of the year. So I want to thank you all for listening and for your support over time. Hubeyb, thanks again for giving us a great closing.
Thank you. You're welcome. Thank you for inviting me.
And
that was my pleasure.
Yeah, to everyone, wonderful holidays. We'll be in touch by email with upcoming talks. They're mostly planned for the spring semester. Stay safe out there, and we look forward to resuming mid-January. So thank you, everyone, and have a wonderful day. Bye.